Let's imagine that we've done a clever piece of Bayesian modelling and now we want to explain our findings. This communication bit is very hard to do well. What makes it hard is that you, the data scientist, have all these rich complex probability models in your head, but you need to explain your findings to someone who barely understands probability, let alone all your clever modelling. Don't think that the problem is that your audience is stupid. They may not understand the intricacies of the model you've built, but as the famous saying goes, all models are wrong. And so why should they have to even bother trying to understand your wrong model? In other words, all the lovely elaborate model you've built is something that exists only in your head. It's not true, and it's not even worth communicating. A model is like underwear. You use it, but it's not decent to show it all in public. This is especially tricky with Bayesian modelling. Bayesian modelling has a massive philosophical overhead, all this business about needing to model unknown quantities as random variables and having to invent a prior. Imagine you're a physicist trying to measure the speed of light or the mass of the Higgs boson, and you try telling your audience, let us treat the speed of light as a random variable. Here is its distribution. No one would put up with that nonsense. And so we need to find friendlier ways to report our posterior distributions. That's what this video is about. Let's imagine we've done a Bayesian analysis of some problem. We started off with the prior distribution for the unknown parameter, call it theta. Then we observed data and we came up with a posterior distribution. How should we report it? It's very tempting to want to report it with a single number, what's called a point estimate. You could look at a distribution like this and say, I'll just tell them the mean. That'll give them a nice simple number they can make sense of. There's another single value readout which is a bit more popular, reporting the value with the highest likelihood. This is known as the maximum a posteriori estimate. But anyone who tries to report a Bayesian analysis with just a single number like this is a hypocrite. Bayesianism is a whole doctrine that says, thou shalt represent uncertainty by random variables. And if you report a single number, you're denying the whole premise of the calculation. There is one small exception, the loss minimizing estimate, which you can read about in the notes. Here's something that's more honest than a point estimate. We could report a confidence interval, saying theta is somewhere in this range. It's common to report what's called a 95% confidence interval, an interval that we're 95% certain contains theta. This is a bit arbitrary, but at least it's honest, because we're clearly communicating that we're uncertain about the true value of theta. If our distribution is all spread out, then the 95% confidence interval will be wide, and if the distribution is tight, then the interval will be narrow. This picture shows the standard way to find the 95% confidence interval. You find cutoff points, low and high, such that the probability of being less than low is 2.5%, and the probability of being more than high is 2.5%, and then the probability of being inside the range low to high is 95%. It's still a bit arbitrary, and we could equally well choose a different 95% confidence interval to report. What you decide to report is up to you. You could find the narrowest 95% confidence interval you can find, for example, if you think that will be most useful to your audience. I'll just say a little bit about how we'd compute these confidence intervals in practice. Let's say we've done the computational Bayes thing and we've got a sample of theta values and associated weights. These weights let us estimate posterior probabilities, for example, to find the conditional probability that theta is less than some threshold low, conditional on the data. To find that, we just sum up the weights for all the sample values theta I that are less than that threshold. This gives us an easy way to compute the 95% confidence interval. We just sort the theta samples, get the cumulative sum of weights, I'll call it capital F, and find the point where the cumulative sum reaches 2.5%. Similarly for the upper end of the threshold. So this is a nice clean way to report uncertainty. But if you look at any science news story, whether it's about COVID or climate, all you ever hear on the news is scientists predict X. Hardly ever scientists give a confidence interval. Why is this? I think it's partly because many scientists don't actually know the maths you need to report uncertainty. I look at all the epidemic modelling around COVID, and I haven't yet seen one study that really tries to quantify how much certainty there is in the predictions. Another reason is that most people wouldn't know what to do with an uncertainty estimate if it hit them in the face. Politicians in the COVID epidemic all want to say, "We're following the science," as if science was capable of producing a single answer. Most politicians simply wouldn't know what to do with a confidence interval. And most journalists don't either, because it would tear apart the simple good-bad dichotomies that they use. Imagine if we had educated journalists and politicians who could say, "There is great uncertainty about this, and we're taking an action which may or may not work, and here's the spread of outcomes we anticipate." And imagine if we had journalists who could challenge them by asking, "And what are the grounds for your uncertainty estimates?" In my own research, I'm working on how we can teach neural networks to not only make predictions, but also to report their level of certainty associated with their predictions. I'm applying it to climate modelling so that we can get a rigorous understanding of uncertainty in climate forecasts. If you're interested in this sort of question, have a look at the AI for Environmental Risk Doctoral Training Centre at Cambridge University, which is looking for master's students who want to apply advanced machine learning ideas to environmental issues.